Once Jack had touched down, the headlines back on Earth shifted, nicknamed Moon Sniper for its stealthy precision. Its whole mission was mainly to demonstrate how precise of a landing we can now pull off. As such, the tiny spacecraft was not meant to survive the extreme conditions of a lunar KN, and yet somehow it has survived 3 baffling scientists. This resilient craft kept waking up and sending back data and images from the lunar surface. Oh, and it's also upside down. I'm Alex Molan, and you're watching Astrum. Join me today on this topsy-turvy ride as we dive into the details of JAXA's first moon landing. What has kept the Moon Sniper functional through 3 lunar KNs, and how much pinpoint landings will change the future of lunar exploration. The Smart Lander for Investigating Moon, also known as SLIM, or Moon Sniper, is a small, lightweight spacecraft about the size of a passenger vehicle. Its mission is to analyze the composition of olivine rocks near the Joly crater, some 200 pound 100 mil south of the Sea of Tranquility, where Neil Armstrong took his famous small step. This landing zone stands on ground ejected by the nearby crater, giving researchers a chance to study lunar rock without having to drill by analyzing the rocks there. JAXA hopes to learn more about the moon's origins, interior, and formation. SIM also carried 2 tiny lunar excursion vehicles, LEV-1 and LEV-2. They were designed to deploy from SLIM and gather some of their own data and photos. Beyond its scientific aims, SLIM is also a showcase of the latest in engineering and mission operations. It aimed to demonstrate how a small explorer could execute accurate lunar landing techniques. This would accelerate the study of the moon and other planets by using a lighter, more precise exploration system, able to land in treacherous rocky terrain too difficult for larger crafts to understand. Why this is a big deal. It helps to have some historical context. The first thing you have to know is that only about 43% of lunar landings are successful. Past lunar missions faced huge limitations in landing accuracy, mainly constrained by technology and the lunar environment. For example, it took the Soviet Union a dozen attempts before they finally landed Luna Chapter 9 on the moon. Similarly, NASA's Ranger series took 6 tries before achieving success. The absence of an atmosphere on the moon means that landers rely solely on engine thrust for descent, complicating the ability to adjust trajectories accurately. During landing, the craft must touch down at near zero speed to ensure no instruments on board get damaged from the impact. Every single Apollo mission landed dangerously close to rocks, craters, or slopes that could have caused serious damage, with very limited ability to make adjustments in real time. The Apollo missions also all landed on the near side of the moon, close to the equator, and in almost perfect lighting conditions to make touchdown as safe as possible. The downside of this, though, is that NASA was always sending spacecraft to the same patch of moon, meaning actual exploration of the surface was limited to this specific landing zone. If we could make a spacecraft capable of landing in a super-precise 000435 landing zone, we could send it to explore whatever and wherever. We, like scientists, would be able to carry out targeted studies of different rocks and soil types without relying on rovers to travel long distances. This reduces mission complexity and cost, while opening avenues to explore new lunar regions. Moon Sniper mission cost $120 million for comparison. The 4 lunar rovers built for Apollo 15, 16, and 17 cost $38 million to develop back in 1972, which would be about $286 million today. More recent rovers, such as the Chandrayaan 2 and Chang 4, cost about $141 million and $180 million respectively. And this is exactly what researchers working on with excellent progress. A landing footprint, also known as a landing ellipse, is the area of uncertainty of a spacecraft's landing zone on an astronomical body back in 1969. Apollo 11's targeting ellipse was 18.5 km by 4.5 km, fast forward to 2013. And China's Chang'e 3 launched with a landing ellipse of 6 km in January 2020. 4. A JAXA lander made Japan the fifth country to land on the moon, touching down just 55 m from the center of its 100 km by 100 km target ellipse, a target 8,325 times smaller than Apollo 11's. Let's take a closer look at the technology that made this possible. Moon Sniper was able to land as precisely as it did thanks to its vision-based navigation system, which JAXA refers to as Smart Eyes, by continuously capturing images of the moon's surface as it descends. The spacecraft is able to locate itself in real time on orbital maps made by data from other lunar rovers, including NASA's LRO, India's Chandrayaan-2, and Japan's Selene. These positions were then matched to a broad map encompassing its location to determine the exact landing site by processing the images in real time. Moon Sniper can adjust its trajectory literally on the fly, enabling it to hit its target with pinpoint accuracy, weighing just 200 kilograms without propellant. A successful slim landing would demonstrate that small, lightweight spacecraft can accomplish complex lunar exploration missions, except slim didn't exactly stick. The landing, while Jackson managed to land the craft on target. It sort of toppled over at the last minute, but after such a precise approach, what caused this grave malfunction? On the 6th of September 2023, JAXA launched Liam on course for the moon. It arrived in orbit on Christmas Day 2023, and eventually approached for landing on January 18, 2024 as Japan watched on. Intently, the approach was live-streamed. One mission team member dubbed the deceleration to landing as expected to be a breathless, numbing 20 minutes of terror as it made its descent to